Hey everyone, and welcome to The Explainer. Today we're looking at something that is literally reshaping our entire digital landscape, the GPU. It's this highly specialized, absolute powerhouse of a chip that's quietly driving the modern world forward. And honestly, if you've paid any attention to tech lately, you've seen those three letters everywhere.
And that brings us to the core question we really want to answer today. Why is the exact same chip that renders the incredible, lifelike worlds in your favorite video games also the primary engine driving this massive artificial intelligence revolution? Well, let's dive right into this. So, originally, engineers designed GPUs to handle the really heavy burden of computer graphics, right? We're talking rendering images, 3D animations, and video processing. But as it turns out, an architecture built to calculate thousands of pixels all at the exact same time is the absolute perfect framework needed to power modern AI and machine learning.
Here is a quick roadmap for our explainer today. We're going to cover 1. What exactly is a GPU? 2. Integrated versus discrete graphics. 3. Speeding up creative workflows. 4. CUDA versus tensor cores. And finally, 5. Choosing your perfect GPU.
Okay, starting right off with Section 1. What is a GPU? The basics. The best way to really wrap your head around this is through a division of labor metaphor. Think of your CPU, your central processing unit, as the master coordinator. It's incredibly smart, it handles general-purpose computing, and it excels at doing sequential tasks very, very quickly. But it can only juggle a few things at once. The GPU, on the other hand, is like a highly specialized team. It's built specifically to process many small calculations simultaneously. This is what we call parallel processing. So while the CPU is busy coordinating your overall operating system, it hands off the massive, parallel mathematical workloads to the GPU.
And the real-world impact of that architecture is just massive. When you're training deep learning models in frameworks like TensorFlow, a GPU can process so much data in parallel that it operates up to 50 times faster than a standard CPU. 50 times. That is a huge leap.
Moving on to Section 2, integrated versus discrete. Let's talk about hardware form factors. Basically, you've got two flavors here. Integrated graphics means the GPU is built directly right into the exact same chip as your processor. It doesn't actually have its own memory. Instead, it shares the system's memory. Now, the massive benefit here is that it uses way less power and generates a lot less heat, which is absolutely perfect for preserving battery life in smaller laptops and many PCs. Discrete graphics, however, is a completely separate card. It has its own dedicated video memory that isn't shared with the CPU at all. Sure, it draws significantly more power and generates a lot more heat, but in exchange, it gives you the raw, massive performance needed for intense rendering and top-tier gaming.
Let's look at Section 3, speeding up creative workflows, and what this actually accomplishes in the real world. Anyone who has ever edited a video knows the absolute agony of a lagging timeline, right? Well, GPU acceleration directly solves this. First step, when you're scrubbing through heavy 4K or even 6K footage, the GPU takes over the decoding task so your playhead glides super smoothly without any of that annoying stuttering. Second step is color grading. Adjusting those color wheels and curves involves doing complex math on literally every single pixel of every frame. A GPU handles this instantly, giving you a real-time preview output. And the third step, accelerating that final export. By sharing the heavy lifting between the CPU and GPU, a render that used to take you half an hour can now be finished in just a fraction of that time.
And honestly, it goes way beyond just basic video editing. Modern GPUs are utilizing these hybrid rendering pipelines and a really cool technology called ray tracing. Ray tracing basically calculates the physical behavior of light in real time. This is completely revolutionizing visual realism across three major industries: gaming, allowing for incredibly cinematic lighting; film production, seamlessly blending CGI right in with live action shots; and architectural visualization, which actually lets clients walk through photorealistic buildings before a single brick is even laid down. All right, Section 4, CUDA versus tensor cores. Let's look at the microarchitecture.
Let's pull off a little magic trick here and zoom way down into the silicon itself. What's really interesting here is the distinction between these two types of cores that often live right next to each other on the exact same NVIDIA GPU. So CUDA cores are your flexible, general-purpose parallel processors working at high precision. They're absolutely fantastic for rendering, physics simulations, and classic machine learning. Tensor cores, on the other hand, well, they really just do one job, but they do it incredibly well. Matrix mathematics for AI deep learning. They use mixed, lower precision, like FP16 or int8, to process massive neural networks incredibly fast.
But remember, hardware is really only half the story here, right? Software is what actually unlocks it. NVIDIA has these inference optimization libraries like TensorRT. What this does is take your trained AI model and it optimizes it specifically for the exact GPU it's running on, combining layers and picking the very best precision formats. The result? Your model can run 2 to 4 times faster without you needing to make any major code changes. It's just an incredible synergy of software seamlessly talking to specialized hardware.
But of course, with all this complex tech, a few myths have popped up that we really need to bust. The first myth is that simply having a higher CUDA core count automatically guarantees better performance. Actually, not necessarily. A massive core count only translates into actual speed if your software is specifically optimized for parallel processing, and crucially, if your task isn't bottlenecked by memory bandwidth. Basically, brute force isn't always the answer.
And here is another massive misconception. The myth goes like this. Because tensor cores use lower mixed precision to achieve their crazy speed, they must be sacrificing the accuracy of the AI model. This is simply not true. Modern machine learning frameworks like PyTorch and TensorFlow automatically and safely manage this precision scaling for you. They grab the speed boost wherever possible, while keeping the final results well within acceptable error margins. So you really do get the best of both worlds. Finally, Section 5. Choosing your perfect GPU.
When you're looking at your own workflow, you might realize you actually need a hybrid approach. Take modern recommender systems, for example, like the ones that magically suggest what movie you should watch next. They actually use both. The CUDA cores on the GPU handle the massive parallel data preprocessing and classical candidate generation algorithms. Then, the tensor cores step right in to accelerate the deep neural network that actually ranks those recommendations. It's pretty much a perfect partnership.
So, the absolutely crucial point boils down to this. You don't need the most expensive GPU. You just need the one that fits your work. If you're strictly doing deep learning and training massive AI models, you absolutely need tensor cores, no question. But if you're doing rendering, simulations, or classical machine learning, a really strong array of CUDA cores will get the job done beautifully. Honestly, identifying your specific bottleneck is infinitely more important than just emptying your wallet for the highest raw specs on the market. Which leaves us with this final thought. We've seen how these specialized parallel powerhouses evolved from just rendering pixels in video games to training the massive neural networks that are literally changing the world today. So, I want you to look at your own creative workflows and machine learning pipelines. What bottleneck is currently slowing you down, and what engine will you choose to break it? Thank you so much for joining me on this explainer. I really hope it brought some clarity to the incredibly fascinating world of GPUs. Keep learning, and we'll see you next time.